MATLAB boundary value problem solver BB4C. Okay. What are the content here? BB4C. What is BB4C? 3-stage laboratory 3A formula. Flow chart, syntax and description, input argument, output argument, the structure solution field, references. BB4C. BB4C is a MATLAB function that solves ordinary value problem. BB4C. What is that? It is a MATLAB function that will solve BB4 for ODEs using finite difference method. What they will use? They will use finite difference method. This fourth order method that implements the 3-stage laboratory 3A formula. What is that? This fourth order method, and it will implement 3-stage laboratory. The solver uses the following 3 input to solve the equation. What they will do? They will use the following 3 input to solve the equation. The function integrates a system of differential equation. This will integrate. This function will integrate BB4C. Will integrate system of differential equation of the form y is equal to function of x comma y, specified by ODE function, subject to the boundary condition by BC function, and the initial solution gets solution initial. Okay. 3-stage laboratory 3A formula. 3-stage laboratory 3A formula. What is this formula? The 3-stage laboratory 3A formula. We have gone through here. Here we have gone through that it will implement 3-stage laboratory 3 formula. So we have to know at least what is 3-stage laboratory 3 formula. The 3-stage laboratory 3 formula is a well-known numerical method. What is this? This is well-known numerical method. This method can easily solve all kind of non-linear and linear ODEs. What they will solve? They will solve all kind of linear and non-linear ODEs. It is developed and with the support of finite difference code in BB4C. How it is going to develop? This is going to develop with the support of finite difference code in BB4C. The study of stability is conducted by employing of the BB4C solver function. What they are saying? The study of stability is conducted by employing of the BB4C solver function. The collocation formula and the collocation polynomial provide a continuous solution, that is fourth order derivative, uniformly in interval equilibrium. Collocation formula and collocation polynomial. This will provide a continuous solution, that is fourth order derivative. How much? Fourth order derivative. Uniformly in interval a, mesh selection and error control are based on the residual of the continuous solution. Mesh selection and error control. These all are based on the mesh selection and error control. Both all are based on the residual of the continuous solution. The tolerance of the relative error is fixed as 10 to the power minus 5. The suitable mesh determination is created and returned in the field solution.x. The suitable mesh determination is created and returned to the solution.x. BB4C return solution, namely solution.y, as a construction. In any case, value of the solution are gotten from the array named solution.y relating to this field solution.x. This. Now, this is the flow chart, like how that thing will work, how we to see flow chart of like laboratory 3A formula, that one. Firstly, declare the variable. We have to declare the variable. Then initialization, initial value we have to give. Discretization the domain. We have to discretize the domain. Then we will call BB4C. It is like system of first order ODE, boundary conditions, and Gauss function, piecewise continuous function. This call BB4C system of first order ODE, boundary condition, Gauss function, piecewise continuous polynomial. BB4C we will call. We will use the system ODE, boundary condition function, and solution, Gauss function, piecewise continuous polynomial. Then eject boundary condition for upper branch. Eject boundary condition for upper branch. For upper branch we will use eject boundary condition. And guess for boundary condition for lower branch. For lower branch we will use guess. Evaluation of the solution by double function. Then we will use double function to to evaluation of solutions. We will evaluate that solution using table function. Then we will get numerical result at last. Syntax and description. What is this? Syntax and description. Like solution, we will use BB4C, solution function, OD function, boundary condition function, solution initial. And BB4C OD function, boundary condition function, solution initial, and options. Solution BB4C OD function, boundary condition function, solution initial. Integrate a system of different allocation of the form y dash equal to function of x comma y. This thing they will integrate. Integrate a system of different allocation of the form y dash equal to function of x comma y, specified by OD function, subject to the boundary condition described by BC function, and the initial solution gas solution initial. This thing. Use the BBP initial function. Use the BBP initial function to create the initial gas solution initial. What? Use the BBP initial function to create the initial gas solution initial. Use the BBP initial function to create the initial gas solution initial. They are saying to use BBP initial function to create the initial gas solution initial, which also define the point at which the boundary condition in the boundary condition function are involved. Solve BB4C OD function boundary condition function solution initial option also uses the integration setting defined by option, which is an argument created by using the BB function. What they are saying, this also uses the integration setting defined by option, which is an argument created using the BB function. So these are the syntax we are using. Mainly we are using these two syntax, and these two syntax they have defined here. Input argument. What are the input we will take? Like first OD function. This is function to solve, and this is a data type function handle. This will handle the function. Function to solve is specified as a function handle that is behind the function to be integrated. This will define the function to be integrated. OD function and boundary condition function must accept the same number of integer variables. What they will do? OD function and BC function will accept the same number of integer variables. What happens? It will accept the same number of input arguments. To code OD function, use the function structure dy dx equal to OD function x comma y for a scalar x and column vector y. The return value dy dt is a column vector of data type single or double that correspond to function x comma y. The return value dy dt is a column vector of data type single or double that is correspond to function of x comma y. OD function must accept both input arguments x and y. OD function is there, no? This will accept both the input argument x also, y also, even if one of the argument is not using the function. Even if you are not using any one of them, yet they will use. Boundary condition function. Then boundary condition function, BC function. Boundary conditions. Boundary condition is specified as a function handler that compute the residual error in the boundary condition. What they will do? Specified as a function handler. It is a function handler. You can see here also. It is written like data type function handler that compute the residual error in the boundary condition. That will compute the what they will compute? They will compute the residual error in the boundary condition. Boundary condition will compute the residual error. Whatever residual error is there in boundary condition, that thing they will compute by boundary condition. OD function and BC function must accept the same number of input arguments. Here, they should accept the same number of input arguments. BC function, OD function must accept the same number of input arguments. To code BC function, use the function structure res equal to BC function YB for column vector YA and YB. To code BC function, use the function structure functional signature res equal to BC function YB for the column vector YA and YB. The return value res is a column vector of data type single or double, of data type single or double that correspond to the residual value of the boundary condition at the boundary point. The return value RES is a column vector of data type single or double that correspond to the residual value of the boundary condition of the boundary point at the boundary point. The return value RES is a column vector of data type single or double that correspond to the residual value of the boundary condition at the boundary point. Solution initial guess of the solution. Solution initial guess of the solution. Use BBB initial to create solution initial. What we have to use? We have to use BBB initial to create solution initial. Unlike initial value problem, a boundary value problem can have. In boundary value problem, what we will get? In boundary value problem can have no solution. Finite number of solutions or infinitely many solutions. These three things can have in boundary value problem. An important part of the progress of solving a BBP is providing a guess for the required solution. An important part of the process of solving a BBP is providing a guess for the required solution. An important part of the process of solving a BBP is providing a guess for the required solution. We will provide the guess. The quality of this guess can be critical. What is the quality? Quality of this guess. Quality of this guess can be critical for the solver performance and even for the successful computation. So we have to give a good quality of guess so that we will get a good performance of that solver and even for a successful computation. Data type is structured data type. It is structured data type. We have to extract that one. Option structure. Option structure. Use the BB set function. Option structure, use the BB set function to create or modify the option structure. What? To create or to modify. To create or to modify the option structure. Data type is structured data type. Output argument. Solution. Output argument solution structure. Output argument. These are the output argument solution structure. We can access the field in the solution with dot indexing such as solution dot. If you want to access the field in solution, then we can use like solution dot field to get the field. The solution that x and comma solution that y is continuous. Is continuous on the interval of integration defined in the initial mesh solution initial x and has a continuous first derivative. What they are saying? The solution dot x and solution dot y is continuous on the interval of integration. These are continuous on the interval of integration defined in the initial mesh solution dot x and has a continuous first derivative. We can use solution with the double function to evaluate the solution at other point in the interval. We can use solution with the double function. We can use solution with the double function to evaluate the solution at other point in the interval. We can use solution with the double function to evaluate the solution at other point in the interval. Output argument. The structure solution has this field. Structure solution had that field. X. Mesh selected by BB4C. This mesh typically contain different points than the initial mesh solution initial. Y. Approximation to YX at the mesh point of select solution dot X. YP, approximation to y dash x at the mesh point of solution that x. Parameter, final value of the unknown parameter is specified in solution parameter. Final value for the unknown parameter is specified in solution dot parameter. Solver, DB force. Which solver we are using? DB force solver we are using. State, computational cost static related to the solution. The number of mesh point. States. What are the data? Computational cost statistics related to the solution. This will define how much computational cost is occurred related to the solution. The number of mesh point, residual error, and number of call to OD function and BC function. The number of mesh point, residual error, and number of calls to OD function and BC function. This all. These are the reference I have used. A title with a BBP solver based on residual control and the MATLAB. So this is given by Champagne and Karjanka. These are the, and Champagne also, Karjanka also given solving boundary value problem for OD, ordinary differential equation in MATLAB with BB forcing. Okay, these are the things. So thank you.